In quantum mechanics, perhaps the most popular result is uncertainty principle, which says that you cannot measure the position and movement of a particle at the same time and exactly. It is impossible to have one number for position where it is and one number for its momentum, you can say its motion. So that is impossible. So that much is the statement, that's correct. But a problem is that many people who know this statement, they do not know where this statement fits in any quantum mechanical scheme. They don't know its quantum mechanical reason. For example, many people are told and then they know and they think that this is a problem about measurements, and measurements are made to be I am state what they think. That they think that it's the only reason for uncertainty principle is that to measure the position of a particle, you have to see it is a microscope, and microscope uses radiation, and to see small things like electron, you have to use a radiation of high wavelengths, which is gamma ray, and also and gamma ray are very energetic. They will disturb its position, and we don't know how much it will disturb, so we don't know its motion, and because it will be disturbed, we don't know its position, and so on. I don't go into details because what I'm saying is that this way of presenting may tell you the correct result, but not through any quantum mechanical route, not any part of any quantum mechanical scheme. So that is, if you know this principle only through this route, you may know a result of quantum mechanics, isolated result of quantum mechanics, but you don't learn quantum mechanics if you know it through this route. So the proper quantum mechanical route is the following, and the proper quantum mechanics is that every particle is a probability wave packet. And the probability has to be in a finite region, and a finite region means it has to be localized. There's the word uncertainty, and I tell you after a few minutes that how the results are related. For the moment you take it, that it is localized means its position should be in a limited region. That means its uncertainty in position should be finite, and that means its probability wave should be zero at infinity. One plane wave is not zero at infinity, but a combination, which is called superposition of many waves, can give you the cancellation at infinity. Cancellation is called destructive interference. Now, I have spoken the word many, and that's a crucial. That means the wave or wavelength should have a variety. Wave number should have a variety, and then de Broglie says that you multiply with h bar, momenta should have a variety. This variety is called uncertainties. So you have uncertainty in position, and to get that you should have uncertainty. That's the variety, is uncertainty in momentum, and uncertainty principle is about these two uncertainties, and that I have already spoken. That uncertainty in wavelength is related by de Broglie principle to uncertainty in momentum. So before I further tell you about the relationship of these two uncertainties, which is Heisenberg Uncertainty principle, I take some time to introduce more on this more familiar position uncertainty, and then I come back to relation with momentum. So with that, I have 5 slides on position uncertainty, and these are the following. That the first question is, what is the origin of this word uncertainty? We know the word localization. It should be a limited region. But why localization is called uncertainty? The reason is the following. that if you are given this graph, here I have not shown you upside down the waves, I have shown you only how the peaks vary, so that you can concentrate on the relevant, maybe relevant information about the wiggling I have dropped in this picture. So if you know the peaks vary this way, and these peaks tell you probability, so that means here is the probability, but here is no probability. So I think I can say that here you are certain in outside. Outside means here. You are certain here. That's it. You cannot get any detection. So that's a certain. So hopefully that paves the way for uncertainty. And now I show it explicitly, the word. Here you are certain, but here you are not certain that where will be detection. When you make first measurement, you are not certain where will be. It can be anywhere. Anywhere is uncertain. That's maybe. And in quantity, this width of this graph where you are uncertain is called uncertainty. I hope that suffices. And meanwhile, I tell you, I said about position, but momentum is similar. It's a momentum, or you should get used to. When I say momentum, there are many words for momentum. It can't be, according to de Broglie, the word can be wavelength, the word can be wave number, or the word can be momentum. They are used interchangeably in quantum mechanics. So I may say K or even wave as momentum. Try to get used to. So momentum, if a momentum graph is there, it will also have a width, and that will be momentum uncertainty. So I mentioned momentum as well, but next for 4 slides I concentrate only on position. Momentum, I will say is similar. So come now, concentrate back to position, and that's I try to relate that uncertainty with the resolution, microscopy kind of thing, which I started this lecture with. And the effort can be the following: that if you have uncertainty, the width of graph is small, and if your detector is small, you have a thing, and the question is whether that will be seen or not. Well, that will be bright or not, that will be shining or not, that will be detected or not. They are all words that mean the same. Then you have to see where is probability wave. If this is a light particle, photon, and its probability wave is here, and in this region there is a large fraction of that, maybe 79% or so. So that means there is a large probability, high chances that this will be seen, this will be detected. So light will strike from it, come to your light, and you will see it. And similarly, there is another light particle will help you seeing that particle. So both will be seen. So you'll have a good resolution picture where every part is seen, maybe something like that. That is if you have your uncertainty is small. But if you have uncertainty large, the same two things, by the way, these are not particles, they are things. The question is that you see the things or not. You see the things if there is a probability of seeing it. But here the probability is it's a probability density graph, and area under the graph is probability. Now here the area under this graph here is a fraction, maybe 21% or so. So 25% chance, that means out of 5 photon particles, one on the average, one will strike. So one time it will be seen, 4 times not seen, and so on. So your pictures about these in actual seeing will be that this may be seen or not seen, 80% not seen, 20% seen. So it will be a blurred picture. So that is if there can be any connection between uncertainty and microscopy. That is trying to connect a popular presentation of uncertainty principle. Now I go back to proper quantum mechanics only. So no more trying to show microscopy, and now proper quantum mechanics only. And the first thing I do it, I said it 5 slides ago, and I repeat it. This time the additional thing is that I show quantitative version as well. So what I repeat is the following, what I said quantum mechanics presentation, is that a wave packet should be localized. Localized means its position uncertainty should be finite. To get that localization, you have to get a cancellation at infinity, and that is possible by many waves. I quickly change the words. Many waves, many wavelengths, many wave number. De Broglie principle says many momenta. Now that I said already 5 slides ago. The new thing I tell you, that these two uncertainties, those two varieties, many here, quantitatively they can be calculated, and I show you next slide how. And the product is greater than a number h bar by 2. Now the reason why this is greater than a finite, although it's a small number, but it's a finite number, it's not 0. The reason is that actually what we are saying is that if you want to get a smaller delta x, this means you want to get a quicker, just quickly, it becomes 0. Then to get quickness, you have a large cancellation here, in a sense large. Large means many waves, a bigger variety in waves, bigger variety in wave numbers here, and bigger variety in momenta. This variety quantitatively is called uncertainty in momentum. So what I'm saying is that if you want to get that small, you have a bigger variety, that large, the product small, large, and the other way around, if you get that large, that small, the product remains greater than equal to h bar by 2. That is statement of Heisenberg uncertainty principle. Now in actual statement quantitative version. Previously I said only a qualitative idea. And now once we have made statement, we do some practice of that. So first can be, the practice is mathematics. And one example, I think even those who do not know mathematics, even they hopefully can understand. That's the simplest example. That if you want to have one momentum, one number, certainly that number, try to pay attention to the words. If you are certain, your uncertainty is 0. So you have certain, it's one momentum, this means one wavelength, de Broglie again. This is one plane wave, the picture is the following. Now, if momentum uncertainty is 0, think of that, what will be position uncertainty? Try to think, maybe I can give you only a few seconds, and I show the result. What Heisenberg says. The result is that if your delta p is approaching to 0, delta x is there. So delta x is, you take delta p on the other side. Delta p is approaching to 0. You have division by 0, that's approaching to infinity, and multiply by h bar by 2. It remains approaching to infinity. Now that's the mathematics. Delta x is approaching to infinity. Try to say in words. And the words can be uncertainty in position is infinite. That means it's totally uncertain. That's another word. And totally uncertain means there's nothing special about any position. Every position is same. Now that much you can understand, hopefully, even without knowing any mathematics. You can appreciate that Heisenberg is correct here. Heisenberg says position uncertainty is infinite. That means you are not certain where it is. And that much, even without mathematics, you can say that plane wave has no preferred position. So every position is same. So it can be any position. When you say, if you understand the word any, that is one verification. Any means uncertainty is infinity. And that what Heisenberg has given you a result, or your own understanding, I leave to you. Now we describe more mathematics, and those who are taking that as a part of a course, they should continue. Others may skip. And if you continue, I have to train you. The next 4 slides are training. How to calculate. The challenge is if you are not given graph. If you are given graph, then it's even those without mathematical understand. If you are given graph, then you just read off the width, and the width is uncertainty. But that is not enough as a part of course. I think in a typical quantum mechanics course, you will not be given a graph, so you will be required to calculate, and the crucial word is calculate, only if you are given formulas. You can learn something from the graph, but eventually you should be able to do without graph. But to start with, for discussion, we can take help of a graph. Now, from the graph, you should learn that if you change height, width doesn't change. So, if there is any constant which will change height of that is not the relevant thing. The relevant topic is width, and width is depends upon the shape. The shape is given by a variable factor. So first thing is, whatever is constant, disregard that. Concentrate on variable factor. In position, variable dependence on position, or variable dependence on k, which we normally call momentum. I have told you many times the reasons. Now furthermore, you concentrate on the easier thing, which is position. You learn from the graph, but what you learn you have to use without graph as well. But furthermore, to start with, you can use the graph to learn the definitions. You have to learn 2 definitions. One is R. R is a finite point, that's a crucial word. To the right of peak value, the peak value is here, where the probability density, psi square is probability density, gets significantly less than its peak value. That's significantly less. So that is definition of R. Left has a similar definition. Hopefully you figure out yourself. The difference is called uncertainty in position. So that this is a definition of left and right. A left is the point where it is significantly less finite, and right is the point is significantly less. Both should be finite. So that's you learn these definitions, and now you apply. Now don't depend upon graph, depend upon only formulas. No longer graph. Get bigger, get elder, and get skilled, whatever it is. Don't take help of graph. For example, your variable factor is that. Don't wait for graph. Think of that. Is there any finite value for which this becomes 0? And this trigonometric sign can become 0 when K is 180 degree. And then if you have to use calculus, you must express in radians. So in radians you will say that this becomes 0 when this is Ka equal to pi, or so plus pi is right, minus pi is left. So green and blue of the previous slide, R and L. You make formula for K, pi by A right, which was green, and minus pi by A left. Their difference is delta K. And de Broglie says you multiply with h bar, that's delta P, and delta P is uncertainty in momentum. That's one training in learning, in reading, in calculating, not given graph, in calculating only from formulas. To get the training, hopefully. Next example is where there is no finite value which gives you 0. That can be Gaussian, for example. You don't have a trigonometric help. If you're thinking that it is 0 at infinity, but infinity cannot be uncertainty, I told you. So this time you have to do something else, and that is that you make a ratio of peak value and arbitrary. Arbitrary is a difficult word, but this means simply as a given formula. You take a formula and ratio of its ratio with peak, and this ratio should be significantly less than 1. For example, here the peak is e power minus x squared should be smallest, namely 0. E power minus 0 is 1, that's the peak. Arbitrary means the given formula. The ratio is this, and you have to select a value of this variable factor or something in it so that it becomes significantly less than 1. And here I hope and you can figure out a normal simple choice is that you make this red one equal to, think of that, and I can't wait, that should, you can choose to be 1. So that will be e power minus 1. So e is, you need not knowing exact value, even if you think it's approximately, my exact value is 2.71. Even if you know this is calculus natural log base is near 3, okay, that's sufficient. E 3 power minus 1 is 1 over 3, that is significantly less than 1. So it's a choice. Different person can have a different choice, but whoever gets significantly less than 1, that is right. There can be a variety, different students may give different answer, but we are verifying an uncertainty. We are not verifying an exact equation. So there can be a variety, and variety by choice, and with our choice we have obtained that red is equal to 1. That means this is simple algebra. Positive root is right, negative root is left, their difference is position uncertainty. And next, I think I have just only one more example for training. And the training doesn't finish, it's a practice, and all the practice I can show is another one is that. If the variable factor is that, x square is variable, is a denominator, so the overall is maximum when this is minimum. The x square is minimum at 0, so that's a peak. You make a ratio of peak divided by it's a peak divided ratio of peak and the variable is this. Okay, sorry, now I say it correctly. The ratio has to be in the numerator. You should have the variable factor, arbitrary actual given formula, 1 over that, because that's 1 over, so numerator will appear as denominator, and the denominator you should have peak. The denominator is already reciprocal, so reciprocal will appear as numerator. So that is the ratio, and you make a natural choice, simple choice of ratio, and that can be, if that is 1 by 2, square is 1 by 4, and that is significantly less than 1. And when that is 1 by 2, that means x square is also a square. So that a square divided by 2 a square is 1 by 2. When a square is a square, take positive root is a, negative root is minus a, the difference is 2a. That is position uncertainty. So that's all training I could give you. And now I just point out and I go to some conclusion, That is first conclusion of the second half. The overall conclusion I will go later. The second half conclusion is that I showed you, I think 4 examples. In every example there was a symbol which appeared in numerator in position and in denominator in momentum uncertainty. The product, in the product that cancels, and the product is a constant number which doesn't change case to case. So that's all. And the conclusion is that proper quantum mechanical way, non-quantum mechanical or popular or semi-quantum mechanical, not that. Proper quantum mechanical way is that uncertainty in position is because a wave packet has to be localized in a limited region. And uncertainty in momentum is to be because to localize you need many waves. The word many means a variety, and the variety is uncertainty. Hopefully that is conveyed. and the product, if you increase one, the other decreases. If you decrease one, the other increases, and the product doesn't vary case to case. It may depend upon your choice. So the result is an uncertainty. But for the moment, what I showed you, that is proportional to h bar. And verification I showed you for a plane wave when delta p was approaching to 0. I hope there maybe everyone without mathematics could understand. And the rest of portion which showed when both were a non-zero finite number, there were calculation how to read off from graph and then calculate from graph. I gave you some training how to make a choice, and you show that their product doesn't vary case to case. Any variable factor cancels out, and the product is in case to case independent, is greater than or equal to h bar by 2. I showed you only the constant, and that's all I could show in this graph. Hopefully I see you in the next graph.